Welcome to Lecture 32, in which we will discuss the Deutsch-Jozsa algorithm, which is a generalization of the Deutsch problem algorithm that we learned about earlier. But first, I'd like to pick up where we left off in Lecture 31. You will recall that the last thing we said in Lecture 31 is the following. The RS element of the W matrix, where we assume that, recall, we have 0 is less than or equal to R is less than or equal to 2 to the n minus 1. And likewise, the same restriction for S, 0 less than or equal to S less than or equal to 2 to the n minus 1. Is given by this formula here. It's 1 over the square root of 2 to the n times negative 1 to the r dot s power. And what we mean by r dot s is we write the Boolean representation, or excuse me, binary representation of r is an n-bit. This is n-bit binary number. Write s is an n-bit binary number, and then we see in how many positions r and s both have a 1, and add those up, and whatever number we come up with, that's equal to r dot s. And then we raise negative 1 to that power. Now, what I would like to do as our first goal for Lecture 32 is to actually demonstrate that this formula is true, or basically prove it. So we'll say prove this formula. Well, recall that W acting on X, wait, now let's see. In order to evaluate W acting on X, we need to know how many qubits X has. And let's say that X has n qubits. So X is an n qubit state. Then in that case, W acting on X is simply H tensor product H tensor product dot 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 tensor product H, and that's n times and now, since X is an n qubit state, we can write this out as X n minus 1, X n minus 2, dot dot dot, X1, X0. And this is the same thing as H acting on X n minus 1, H acting on X n minus 2, dot 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 H acting on X1 tensor product H acting on X0. And keep in mind now that each one of these qubits in X has a value of either 0 or 1. Now, let's step aside for a moment and let's calculate X acting on, let's say, lambda, where lambda can be either 0 or 1. Well, if lambda is equal to 0, we know that h of 0 is 1 over the square root of 2 of 0 plus 1 over square root of 2, 1. And this is if lambda equals 0. And on the other hand, if lambda is equal to 1, we get 1 over the square root of 2, 0, minus 1 over square root of 2, 1. Now, if you look at this for a moment, you will see that this could be written more compactly in the following way. H operating on lambda is equal to the sum Z equals 0 to 1 of 1. Well, let's just put the square root of 2 in the bottom. And then we can say negative 1 to the lambda z power. Now let's check that and make sure that it looks right. Okay, check. Well, this in the case lambda equals 0, this formula gives h of 0 equals sum z equals 0 to 1 of negative 1, and then since lambda is equal to 0, this lambda z term here in the top just becomes 0 over square root of 2. Oh, and sorry, I left out one thing here. We should have a z here, and likewise here. And so when we now go ahead and write out the terms in this summation in the top, of course, negative 1 to the 0 is just 1. So we have sum z equals 0 to 1 of z over square root of 2. And this would give us the correct answer. H operating on 0 is 0 plus 1 over square root of 2. So this formula does indeed work when lambda is equal to 0. And now let's check it for lambda equals 1. So in the case lambda equals 1, this formula gives h of 1 equals sum z equals 0 to 1 of -1. And now, since lambda is equal to 1, this is just -1 to the z power times z. And now when we expand that out, okay, the z equals 0 term in this summation will give us -1 to the 0 power, which is +1 times 0. So we'll get 0. And then when we go to the z equals 1 term, we will get -1 to the first power, which is -1, and then 1 here. So minus 1 over square root of 2. And of course, that's correct as well. So that verifies that this formula is correct. This formula right here is correct, regardless of whether lambda is 0 or 1. Now let's go back up here, now that's for 1 qubit, but now notice that for this general case of an n-qubit state, we have decomposed that into the tensor product, this n-fold tensor product of H acting on a number of different 1 qubit states. And so what we will get is the following. Let's repeat that formula down here, and then we'll continue with it. So I'll just take this formula right here. Let's see if we can paste it down here. Let's try this again. Okay. So now let's pick up with this work and see if we can get the proof that we're looking for. Okay, so in view of the work that we just did, we can write for h of xn minus 1, let's call that the sum of z n minus 1 equals 0 to 1 of -1 to the x n minus 1 z n minus 1 z n minus 1. Now all we're doing here, there's no tricks. This is just this formula right here, which we've already verified. But in the place of lambda, we have xn minus 1, and in the case of z, z is just a index here in this sum, so we don't have to use z. We could call it anything we wish, and we'll call it z sub n minus 1 here. So for h of xn minus 1, this is what we'll get. And then for h of xn minus 2, we will get sum, and here in this one, we'll let the index be z n minus 2, ranging from 0 to 1, and -1, And here, this time we'll have x n minus 2 times z n minus 2, and then the vector, the state will be, or z n minus 2, and then dot dot dot. Now for h of x1, okay, this will be, oh, and of course in each case I need to have a square root of 2 in the bottom. Square root of 2. Because of course you can see that up here in our formula, the square root of 2. So now h of x1 will give us some z1 will pick to be the index in this case. z1 equals 0 to 1, negative 1 to the x1 z1 power, z1 over square root of 2. And then finally, for h of x0, we will have summation z0 equals 0 to 1, negative 1 to the x0 z0 power z0 over square root of 2. And that's equal to w of x, where x is the n-qubit state, xn minus 1, xn minus 2, dot dot dot, x1, x0. Now, if we put this all together, this will be the same thing as 1 over the square root of 2 to the nth power, because we have square root of 2 in different times. So this is the square root of 2 to the n in the bottom. And then what do we have in the top? Well, we have the sum zn minus 1 equals 0 to 1, sum zn minus 2 equals 0 to 1, dot dot dot, sum z1 equals 0 to 1, sum z0 equals 0 to 1, and then we'll have negative 1 to the xn minus 1 zn minus 1 plus xn minus 2 zn minus 2 plus dot 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 plus x1 z1 plus x0 z0, and then when we put all these 1-qubit states, when we take the tensor product of all of them, we get the n-qubit state z n minus 1, z n minus 2, dot dot dot, z1 z0. Now, for the next part of our reasoning, let's make the following observation. What is this exponent for negative 1 equal to? If we take xn minus 1 times zn minus 1 plus xn minus 2 times zn minus 2 plus dot 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 plus x1 z1 plus x0 z0, what is that equal to? Well, let's write everything else out. that is simply equal to x dot z. And think about this. Think of writing out x as a n-bit binary number, and of course we have it right here. It is xn minus 1, xn minus 2, x1, x0. That's x written out as an n-bit binary number. And z written out as an n-bit binary number is right here. And I claim that the value of this exponent will simply be equal to the number of positions in which x and z both have a 1. Now, how can we see that? Well, in any position where one of these is equal to 0, like for instance, let's say that one of them or both of them, either one or both of them, have a 0 in this n minus 1 position, then one of these or both of these numbers here of xn minus 1 and zn minus 1, one or both of them would be 0, in which case this term would be 0 and would not contribute to this sum. The only way that any one of these terms will contribute to this sum up here in the exponent, this exponent is a sum of terms, and the only way that any of those terms contributes to the sum is what? If both of the terms are equal, both of the individual terms in that term here, if both of these is equal to 1. So this summation here is just a summation of the number of positions in which x and z both have a 1. And of course that's what we called in our last lecture x dot z. So we now see that w acting on an arbitrary n-qubit state x is equal to 1 over the square root of 2 to the n times the summation. And notice that what is this summation here really? It is the summation over all possible n-qubit states. Or let's say, let me rephrase that. It's the summation over all of the elements in the standard basis for an n-qubit state. Because you see that we have all the possibilities here. We have zn minus 1 must assume both values 0 and 1. Zn minus 2 must assume both values 0 and 1, and so on all the way down to z0. So we will cover all of the possible elements in the standard basis for n-qubit states. So this is just summing up over all of those 2 to the n terms in that basis, is summing up over all of them, and each one is getting multiplied by -1 to the x dot z power. Now to finish off our proof, notice that if we let x remember, this formula here is good for an arbitrary n-qubit state. This formula here is good for an arbitrary n-qubit state. So if we let x equal, let's say r, where r is one of the elements of the standard basis, then we get w of x, w of r is equal to 1 over the square root of 2 to the n times the sum zn minus 1 equals 0 to 1, sum zn minus 2 equals 0 to 1, sum z1 equals 0 to 1, sum z0 equals 0 to 1 of negative 1 to the r dot z power times z n minus 1, z n minus 2, z 1, z 0. But if r, remember we're assuming here that r is one of the elements of the standard basis. So in that case, this is telling us here really the terms in the corresponding column of the W matrix. What I mean is that when we choose all zeros here, for zn minus 1 equals 0, zn minus 2 equals 0, all the way to z0 equals 0, and then we get 0, 0, all zeros here. Of course, all zeros there is the first element in the standard basis for n-qubit states. We have n zeros. That's the first element in the standard basis for n-qubit states. And so this would be, when we choose all zeros there, then the coefficient that we get right here would be the top number, the number that would appear at the very top of the W matrix in column R. Then the number that would appear right below that would be the number that we would get when we choose all zeros except z0 equals 1. Because here we would have 0, 0, 0, 0, and then a 1, and so that corresponds to the second term in that column. And of course here, then we would need to adjust that appropriately. And so on for each term in that column. All we would need to do, we're going to pick out of all of these sums. Keep in mind, each one of these sums contributes 2 terms. So there's 2 here, and so on up to 2 there. And there are n summation signs. So we have 2 to the n terms, which is of course, that's not surprising because W is a, since we're talking about n-qubit states here, W is a 2 to the n by 2 to the n matrix. Just like when n is equal to 1, it's a 2 by 2 matrix. When n is equal to 2, it's a 4 by 4 matrix. When n is equal to 3, it's an 8 by 8 matrix. It's 2 to the n by 2 to the n. So we have 2 to the n terms here. If we expanded all this out, picking all the possible values for z0, z1, up to zn minus 2, up to zn minus 1, we get all together 2 to the n terms, and we'd get all the possible terms in the standard basis for an n-qubit state, and each one of them would have a coefficient of the form -1 to the r dot z power over the square root of 2 to the n. And so from this we see that WRS is equal to -1 to the r dot s over the square root of 2 to the n. That's just picking out one particular term. The S, you're interested in the S row of column R, so you're picking out one of these, and whichever one you pick, then you will write out that value up here as a n-bit binary number, take the dot product with R. That's what this is basically amounting to, is taking the dot product with R, and then divide by the square root of 2 to the n. So this is actually proving, and this is an interesting proof, but it's really quite straightforward. I wish I could take the credit for it, but this is actually an idea that I saw outlined in the Nielsen and Chuang textbook that we'll be using next semester in our follow-up course. But this is a way to prove this formula this formula here at the top of the page that we talked about at the end of lecture 31. Well, now you see how to prove it. And by the way, just switching over to lecture 31 for just a moment. You will recall that in lecture 31, here's an excerpt from lecture 31. Another result that we talked about in that case, in that lecture, was to say W of 0, and here 0 is the 0 state for it's a 0 n qubit state. So in other words, we have n zeros here. This is understood to be n zeros, and that's 1 over square root of n times the sum x equals 0 to capital N minus 1 of x. Well, we demonstrated the plausibility of this formula here for different cases, but we did not prove it. Well, I'll just go ahead. I won't actually prove this, but this one could be proven now in exactly the same way that we proved this formula right here. In other words, write out this W as H tensor product H n times, and each one of those will be acting on a 0, since this is the state with n zeros, and then put all those together and you will get the right hand side after just a little bit of manipulation. So this idea, this approach to evaluating W is very powerful. So now let's return to lecture 32 and see how this formula is going to help us. And I'll keep it, actually I believe that I want to keep it in this form right here for the moment. This is the form I want to use in going forward. Now we're ready to begin talking about the Deutsch-Jozsa algorithm. And let's first start with this reminder. Remember that in the Deutsch problem, Bob has a function f of one variable, one Boolean variable. Alice wants to find out with just one query, whether or not this function is a constant function. With classical methods, she can't do this. But with quantum methods, she can, as we have seen. Now, in the Deutsch-Jozsa algorithm, Bob has a function f of n Boolean variables. It is either constant or balanced. Let me actually rephrase that sentence just to make this clear. It is assumed to be either constant or balanced. Now, what do we mean by balanced? Balanced means that f has a value of 0 for half of the possible combinations of inputs, and 1 for the other half. For example, in the case n equals 2, we might have f of 0, 0 equals 1, f of 1, let's say 0, 1 equals 1, f of 1, 0 equals 0, and f of 1, 1 equals 0. That's one possible function, one possible balanced function of two Boolean variables. But of course, another possibility would be f of 0, 0 equals 1, f of 0, 1 equals 0, f of 1, 0 equals 1, f of 1, 1 equals 0. or dot dot dot. So the word balance just means, as the word suggests, the function is balanced out. Half the time it's equal to 0, and half the time it's equal to 1. Whereas a constant function is either always 0 or always equal to 1. So these it's guaranteed here that Bob has a function of one of these two types. It's either a constant function or it is a balanced function, and Alice wants to know which is the case. Now, let's think about classically how she would go about doing this. Since the function requires n inputs, Alice could send Bob a string of n binary values, 0 or 1. Now, let's suppose that, like for instance here in this case, for n equals 2, let's suppose that we were in this first case. If she sent 0 and 0, then Bob would send her back the value of 1. And then if she sent another string of 2 bits, let's say 0 and 1, Bob would again send her back a 1. So you see, for the first two values, the first two strings, if she's just going up, counting in the usual binary fashion, 0, 0, 0, 1, she might begin to get the impression that this function is a constant function. It would only be when she gave him the next one, 1, 0, that she would find out that he would send her back a 0, and therefore once she saw a 0, then she would know for sure that this function was no longer constant, and therefore because she's aware of this guarantee that the function is either constant or balanced, so she would only at that point realize that it was a balanced function. So that means, let's count this. We have altogether 2 to the n different values here, or different 2 to the n different combinations of the inputs for f. And Alice might need as many as half of those plus one more. So 2 to the n minus 1 plus 1 is the guarantee. Alice will know in 2 to the n minus 1 plus 1. She will certainly know in if she sends Bob 2 to the n minus 1 plus 1. So let's put it like this. So classically, it might take Alice as many as 2 to the n minus 1 plus 1 queries to determine if the function is constant or balanced. Now, of course, in the second case, if Alice took that same strategy of just counting upwards, 0, 0, 0, 1, 1, 0, 1, 1, and if the function were this second function, then she would know sooner. She wouldn't know after one query, because after 0, 0, she would just Bob would send her back a 1, and that information alone doesn't tell her if the function is balanced or constant. But then with her very next query, when she sent Bob a 0 and a 1, and he sends back a 0, since that's different from the first value of 1, now she would know it's not a constant function, and therefore it has to be a balanced function. So in that case, she would know more quickly than 2 to the n minus 1 plus 1 queries. But of course, with this one, let's say that instead of going in that order, if she went 0, 0, and then 1, 0, she'd get a 1 and a 1, and so she would need a third query, so she'd be back. So it just depends on her guessing strategy as to how many guesses it takes her. But the point is, she, of course, since she doesn't know what the function is, she might be unlucky, and the only guarantee is guaranteed that in 2 to the n minus 1 plus 1 queries, and it's guaranteed that she can find out in that many queries. She might be able to find out more quickly than that, but maybe not. This is the worst case, and that's classically speaking. But now, just as we did with the Deutsch problem, here with the Deutsch-Jozsa algorithm, we want to see how Alice could do this with just one query using quantum methods. So let's say, how can Alice determine whether F is constant or balanced using a quantum approach? And that is what we will discuss now. Since we're already at the 47-minute mark, let's go ahead and stop this lecture, and then in lecture 33 we will jump right into the answer of explaining the Deutsch-Jozsa algorithm and exactly how this can be done. We have all the preliminaries now in place. We understand, I hope, the statement of the problem, and so in lecture 33 we will jump right into the solution. Now, certainly I invite you to be thinking about this ahead of time, because it's just a generalization of what we've already talked about with the Deutsch problem. So I would encourage you to try to figure this out on your own, but certainly I hope to understand if you can't. So don't worry too much about it, but that's what we'll be looking forward to next time. And so since we have not completed this topic and aren't ready to try to do any problems related to it, let's take this opportunity for our problems for today to look at, to begin to review for the final exam. And so all of the in-lecture problems are related to this following situation. We say, consider the state, this should be the state, consider the state C, which is equal to A00 plus B01 plus C10 plus D11, where A, B, C, and D are all real positive numbers. Alice measures the first qubit using the standard basis, and Bob measures the second using the standard basis. If Alice measures 0, the probability that Bob measures 0 is 30%. If Alice measures 1, the probability that Bob measures 0 is 40%. So the first question is, which statement is true? A, C must be entangled. B, C must be unentangled. Or C, the information given is insufficient to determine whether C is entangled or unentangled. So decide which one of those three statements is true. And then for the rest of the problems, it says, assume for the remaining problems that the probability that Alice measures 1 is 60%. Everything else already given is true, but now you're given this one extra piece of information, which is that the probability that Alice measures 1 is 60%. Now, do not use that piece of information to answer 32.1. That is something that you do not know, and answering 32.1. So 32.1 is based only on this top information. But then the rest of these are based on the information at the top plus this one additional fact, which is the probability, the probability that Alice measures 1 is 60%. Now, given all this information plus this extra fact, you should be able to find A, B, C, and D. And so that's what you need to do in problems 32.2, 3, 4, and 5. And so that will begin to get you in the process of reviewing for the final exam. And once again then, in the next lecture, we will jump right into showing how the Deutsch-Jozsa algorithm can be used to determine in just one query whether Bob's function of n Boolean variables is constant or balanced. And that concludes lecture 32. And so good luck.